Welcome to Spring LIB.
This is the answer to Chapter 12, problem number 54 from the Smith Organic Chemistry textbook. So for this problem, we're asked to solve the structure of three different molecules, given some information about the molecules. I particularly like this kind of problem. In my experience, you always get a problem like this on a midterm or a final in an undergraduate organic chemistry course. And so first we're asked to solve the structure of molecule A. And the information that we're given for molecule A is that its formula is C8H12, and that ozonolysis of molecule A gives us this dialdehyde right here, and only this dialdehyde. And so just from that piece of information, that oxidative cleavage gives us just this molecule, we know that A has to be symmetric. And so the first thing that we might think to do would be to combine two of these dialdehyde molecules. And doing so would give us this 8-membered ring with 2 double bonds in it. And so if you count your carbons and hydrogens, that does fulfill the formula C8H12. And then another good thing to do is to calculate the hydrogen deficiency index, or the unsaturation number, as it's also known. And when you do that, you get an unsaturation number of 3. And so this tells us that there are 3 double bonds, 3 rings, or some combination of double bonds and rings adding up to 3 in the molecule. And we see that what I've drawn here for A does fulfill that. We have 1 ring and we have 2 double bonds for a total of 3. And so this is the answer for A. So then we're asked to solve the structure of 2 molecules, B and C. And the information that we're given this time is that B has a molecular formula of C6H10. And we're also told that hydrogenation with hydrogen gas and palladium gives this molecule from B. So we know that this is the basic skeleton of B, but that there are probably double bonds somewhere in the molecule. And so when we calculate the hydrogen deficiency index for B with the formula that we were given, we find an unsaturation number of 2. And so we know that there are 2 double bonds or perhaps a triple bond in B. And the other piece of information that we're given is that when B is treated with sodium amide and then methyl iodide, we get molecule C. And molecule C, we're told, has this formula here, C7H12, and its hydrogen deficiency index is also 2. And so the only reaction that we've really seen so far with sodium amide is deprotonating a terminal alkyne, and then using an alkyl halide to form a new carbon-carbon bond between the terminal carbon in the alkyne and whatever is attached to the alkyl halide. And so if we look at these formulas, we see that does make sense. And so given what we know so far, we can use this skeletal structure for B that we determined earlier, and we can put the alkyne at the end. And so this is B. And then if you were to treat this molecule B with sodium amide and then methyl iodide, you would get this molecule C, and C, what we've drawn here, does fulfill the formula that the problem gave us. And so these answers are correct as well for B and C. And that is problem number 54.